Check, check. All right, we're back. I think we're working now, so let's try to get into this video.
Hey, my name is Mike. I'm a developer from Philadelphia, and in this video, we're going to answer the question, why object-oriented programming? In order to answer that question, we'll take a look at object-oriented programming as a programming paradigm and compare it to two other popular programming paradigms. We'll also take a look at the 4 pillars of object orientation. So without further ado, let's get into the video and get started. In the early days of computing, most programs developers were writing were simple and fairly straightforward. But as computers started to become faster and more powerful, the complexity of the programs developers were writing increased. So as code became more and more complex, programming languages and best practices evolved to suit the needs of developers. Eventually, these evolutions in languages and best practices led to what we now call programming paradigms. A programming paradigm is a specific style of organizing and writing programs with the goal of increased organization, less bugs, and better code maintainability. In this video, I'll be discussing one of the most popular programming paradigms used today, object orientation. We'll take a look at some of the features of object orientation and look at how it compares to other popular paradigms. First, it'll help to have an example we can use to illustrate these concepts. So let's imagine a simple to-do list program. This program would allow users to keep track of tasks they need to complete throughout their day. Each task would have a description and a status, whether or not it's complete. Now, before we dive into object orientation, let's take a step back and examine what exactly makes up a program. All programs have data and behavior. The data is what the program knows. In the case of our to-do list, that's the name of the tasks and whether or not they're complete. The behavior is what the program can do with its data. In our to-do list program, we can toggle whether or not a task is complete. So we can toggle a task as complete or incomplete. So in this case, we have 2 pieces of data and 1 behavior. This data and behavior makes up the core of what our program will do. To really get a grasp on object orientation as a programming paradigm, let's take a look at it alongside 2 other popular programming paradigms, procedural programming and functional programming. In procedural programming, the data and the behaviors are spread out into the same set of step-by-step instructions. When we need to use the behavior, in this case, toggling a to-do task, we can manipulate the data directly, thus changing the overall state of our application. In procedural programming, the order of our code matters very much, and our data is mutated directly as the program carries out its behavior. In functional programming, the data and the behavior are kept separate. When we want to use our behavior and toggle the to-do task, instead of mutating the data directly, our behavior will be abstracted into a pure function, which takes our data in as an input.
So I'm just trying to really understand this. So procedural, you'd have task description equals do dishes. Task is complete is equal to false. Toggle complete, you're passing task is complete, so false, to toggle complete. And if you print task is complete, then output's true. So we're assuming here that we have a predefined function called toggle complete that just changes the value of whatever it's passed.
We can manipulate the data directly, thus changing the overall state of our application. In procedural programming, the order of our code matters very much, and our data is mutated directly as the program carries out its behavior. In functional programming, the data and the behavior are kept separate. When we want to use our behavior and toggle the to-do task, instead of mutating the data directly,
So here we have a list task equals do dishes, comma, false. And we have this toggle task variable is equal to, assuming we define this function pure toggle complete, it takes in the task and it prints toggled task, which is a list that has something in it. I'm a little bit confused about what this seems strange. So procedural is very simple, like just linear, right? Whereas it seems like functional is meant to break down everything into functions.
2 other popular programming paradigms, procedural programming and functional programming. In procedural programming, the data and the behaviors are spread out into the same set of step-by-step instructions. When we need to use the behavior, in this case, toggling a to-do task, we can manipulate the data directly, thus changing the overall state of our application. In procedural programming, the order of our code matters very much, and our data is mutated directly as the program carries out its behavior. In functional programming, the data and the behavior are kept separate. When we want to use our behavior and toggle the to-do task, instead of mutating the data directly, our behavior will be abstracted into a pure function, which takes our data in as an input and returns an updated copy of our data as an output. In functional programming, we never mutate the data directly. Instead, we rely on pure functions to return a new copy of the updated data. That's a little about procedural and functional programming paradigms. Now let's see how object orientation handles data and behaviors. In object-oriented programming, the data and the behavior is grouped together in objects. An object is a special entity in our code which combines all of the data or attributes as well as all of the behaviors or methods into an easy-to-use container. When we want to access the data or use the behaviors, we do so through the object. In the case of the to-do app, we might create a task object for each.
So here we have task is a new task object, which has do dishes and false. And then task got toggle complete. So we're assuming we define a function called toggle complete within our task class. And then we can print task.isComplete true. So also assuming that we've defined a variable in our task class called isComplete that stores whether it's true, or maybe I guess toggle complete is a function that kind of changes the value of isComplete. And so when we run task toggle complete, it just changes the value of the isComplete variable. Whether it's true, it changes it to false, or if it's false, it changes it to true. And here we see new task, do dishes, and false. So we pass in false. So I guess that makes sense.
Each task in our program container. When we want to access a special entity in our code, it handles data and behaviors. In object-oriented programming, the data and the behavior is grouped together in objects. An object is a special entity in our code which combines all of the data.
I see here now. So we have a variable called description, and we're passing in a string do dishes. we have a variable called isComplete, and we're passing it a string false. So I guess in the class definition for task, you're just setting it up with a variable description, which I guess would be like self.description equals description, and you're setting it up with a variable called isComplete, which I'm guessing would be self.isComplete equals isComplete, meaning it's the values of description and isComplete within the function are determined by the parameters that are sent into the function. Let's say if it's if it's a keyword argument, you could do description equals do dishes, or isComplete equals false. Or if it's a, what's the other term? I forget, but like in ordered arguments, placement arguments? I forget. But anyway, the first one is description, so yeah, makes sense. And it also has this toggle complete function within it, which seems to just change the value of whatever isComplete is set to.
Attributes, as well as all the behaviors or methods, into an easy-to-use container. When we want to access the data or use the behaviors, we do so through the object. In the case of the To-Do app, we might create a task object for each task in our program, which would keep track of the name and complete status of the task, and would also know how to toggle it. Now that we've taken a look at object orientation compared to other popular paradigms like procedural and functional programming, let's dive a bit deeper and talk about the 4 pillars of object orientation. These are 4 characteristics of object orientation, namely encapsulation, abstraction, inheritance, and polymorphism.
The 4 pillars of object orientation are encapsulation, abstraction, inheritance, and polymorphism,
which provide endless benefits to developers and are responsible for object-oriented programming success in the development world. The first pillar is encapsulation. Now you'll recall when we created our to-do list using object orientation, we combined all of the data and behavior for a to-do task into a single object. In reality, we would define a task class and then create task objects based on what's in the class. These objects will then keep track.
In reality, we would define a class object, task description is a string, isComplete is a boolean, and toggle complete is a function, and then define class
A to-do task into a single object. In reality, we would define a task class and then create task objects based on what's in the class.
And then create task objects based on the class. So we define the class task, and then we can create task 1 is a new task, and we can pass it do dishes and false. Or we could create task 2 as a new task, and we could pass it walk dog and true.
These objects will then keep track of the to-do list description, complete status, and also the functionality around toggling the complete status in one simple container. The first pillar, encapsulation, refers to an object's ability to do exactly this, to bundle together related data and behavior and limit data scope.
Encapsulation refers to what do you say exactly?
The first pillar, encapsulation, refers to an object's ability to do exactly this, to bundle together related data and behavior and limit data scope.
Encapsulation refers to an object's ability to bundle together related data and behavior and limit data scope. Encapsulation refers to an object's ability to bundle together related data and behavior and limit data scope. An object's encapsulation refers to its ability to bundle together related data and behavior and limit data scope.
So not only does keeping the data and behavior together like this make it easy for programmers to make sense of the data and behavior involved in a task, it also prevents code outside the object from seeing how it works or modifying it in undesirable ways. The task is now encapsulated into its own entity.
It also prevents data. Sorry, what did he say?
It also prevents code outside the object from seeing how it works or modifying it in.
It prevents code outside the object from seeing how it works or modifying it in undesirable ways.
The task is now encapsulated into its own entity and can choose how it wants to interact with other code and what aspects of its behavior it wants to expose. Without encapsulation, you'd still need to keep track of the data and behavior related to a task, but it would be all jumbled throughout your program. You might have the task's name in one place, its complete status in another, and the function for toggling it in another. And that's just for one task. Imagine if your program needed to keep track of hundreds or thousands of tasks. Your code would soon resemble a plate of spaghetti. Encapsulation bundles data and behavior together that should
Encapsulation bundles data and behaviors together.
be together.
Should be together.
It makes it easy for that data and behavior to be used by other parts
It makes it easy for that data and behavior to be used by other parts
of our code.
of
The
our
second pillar of
code.
object orientation is abstraction. Abstraction is object-oriented programming's ability to hide complex logic from the user.
Abstraction is object-oriented programming's ability to hide complex logic from the user,
Making the code we write easier to use in other places.
making the code we write easier to use in other places. Abstraction is object-oriented programming's ability to hide.
Is abstraction. Abstraction is object-oriented programming's ability to hide complex logic from the user.
Abstraction is object-oriented programming's ability to hide complex logic from the user,
Making the code we write easier to use in other places.
making the code we write easier to use in other places. Abstraction is object-oriented programming's ability to hide complex logic from the user, making the code we write easier to use in other places.
A good example of abstraction in the real world is sending an email. When you send an email, you open up your email client, type out a message, and click send. It's as simple as that. You don't need to know anything about email servers or the way emails get encoded or formatted or transferred over the internet. That entire process is abstracted away from you, and you just have to hit the send button. By placing all the complex logic of our programs in classes, just like with emails, we're able to abstract it away from the people using our code and make everyone's life easier. In our task class, we've abstracted away the logic of toggling the isComplete state. In reality, to toggle this value, we may need some complex code, maybe an if statement to check the current complete status, some logic for updating that value, or some other checks to like maybe make sure the current user has permission to toggle it.
If user.can edit, if this dot is complete, return false, return true, else prompt for login.
But if we're using a task object in our code, none of that matters. All we need to do is call the object's toggle complete method, and we get the same effect. We don't need to know anything about how this is getting toggled or the logic behind when it can and can't be
My task dot toggle complete.
toggled. We just call the class method and it works. In this case, we've abstracted away the logic behind toggling the complete status on a task, ultimately making it easier for other pieces of code to perform that action. Now that we've taken a look at the first two pillars, let's take a look at the third, which is inheritance. In object-oriented programming, inheritance allows a class to inherit all of the functionality of another class.
Inheritance allows a class to inherit all of the functionality of another class.
This allows us to share code between multiple classes and reduce the amount of code that needs to be written over.
This allows us to share code between classes and reduce the amount of code that needs to be written overall.
Inheritance allows a class to inherit
Inheritance allows a class to
all of the
inherit
functionality
all of the functionality
another class.
of another class.
This allows us to share code between
This allows us to share code
multiple
between
classes
multiple
and reduce the amount of code
classes and
that needs to be
reduce the
written
amount
overall.
of code that needs to be written overall.
This allows a class to inherit all of the functionality
In object-oriented programming, inheritance allows a class to inherit all of the functionality of another class.
This allows us to share code between multiple classes
code between multiple classes
and reduce the amount of code that needs to be
the
written
amount of code that needs to be written overall.
Now that we built version 1 of our to-do app, let's suppose we wanted to add an additional type of task to the app. This would work like a normal task, except it would have a deadline on it. This special type of task can be called a deadline task. In addition to having all the attributes and methods of the normal task, the deadline task will also have a deadline attribute, which would be a date or a time, and an is overdue method, which would tell you whether or not it's currently overdue.
So first we define a class called task with variables description and is complete and a function toggle complete, and then we extend that task class with a new class deadline task, which inherits task but also has a variable deadline and a function is overdue.
Now you might think that in order to create this new deadline task, we'll have to copy and paste all of the code from the task class into the deadline task class. But thanks to inheritance, we actually don't. As I mentioned, inheritance allows a class to inherit all of the attributes and functionality of another class. Therefore, we can use inheritance to have the deadline task inherit all of the attributes and functionality of the task class. This means that we don't have to re-implement or rewrite any of that logic. All of that will automatically be available to any of the code interacting with a deadline task. Therefore, users of the deadline task objects will be able to work with them and toggle them complete or incomplete, just like with a normal task, without us having to rewrite any of that code. Generally, inheritance works best in situations like this, where you have an entity like a deadline task, which is just a more specific version of another entity, like our task class.
Inheritance works best when you have a class which is just a more specific version of another class. Inheritance works best when you have an entity which is just a more specific version of another entity.
The final pillar of object-oriented programming is polymorphism.
Inheritance works best when you want to define an entity that's just a more specific version of another entity.
The word polymorphism literally means having multiple forms.
Polymorphism means having multiple forms. Polymorphism means having multiple forms. Polymorphism means having multiple forms.
In object-oriented programming, when we use inheritance in our classes, we can take advantage of polymorphism when using these classes. To help make sense of this, let's take a close look at our two tasks. First, we have a general task defined in the task class. Then we have a deadline task, a more specific type of task, which inherits all the functionality and attributes of the task class. Let's suppose we had two objects. One is a task called myTask, and the other is a deadline task called myDeadlineTask. In order to understand polymorphism, we have to look at these objects in terms of their data types. Remember that when we create a class, we're actually creating a new data type. The first object, myTask, is the task data type.
When we create a class, we're actually creating a new data type. So instead of, int number equals 5 or string name equals geo, you do task myTask equals take out garbage and true.
It's an implementation of the task class, which makes it a task type. The second object, myDeadlineTask, is a deadline task data type. It implements the deadline class. But because the deadline task inherits all of the attributes and functionality of the task class, the myDeadlineTask object is also a task data type. If you think about it, this makes sense. The myDeadlineTask object has all the same attributes and methods as the myTask object, along with a few more specific ones related to deadlines. So any code that's designed to work with a task object will also be able to work with a deadline task object. This, in a nutshell, is polymorphism. It's what allows us to use either a normal task object or a more specific deadline task object in our programs interchangeably. So anywhere a task object would go, a deadline task could also go. So there we have it, the 4 pillars of object-oriented programming. We have encapsulation, which allows us to bundle together related data and behavior and limit data scope.
Encapsulation allows us to bundle together related data and behavior and limit data scope. Encapsulation allows us to bundle together related data and behavior and limit data scope. Encapsulation allows us to bundle together related data and behavior and limit data scope.
Abstraction, which allows us to hide complex logic from the user and make our code more accessible.
Abstraction allows us to hide complex logic from the user and make the code more accessible. Abstraction allows us to hide complex logic from the user and make the code more accessible. Abstraction allows us to hide complex logic from the user and make the code more accessible.
Inheritance, where a class can inherit all the functionality and attributes of another class, and polymorphism.
Inheritance is where a class can inherit all of the attributes and functionality of another class. Inheritance is where one class can inherit all of the attributes and functionality of another class. Inheritance is where a class can inherit all of the attributes and functionality from another class.
Polymorphism, the idea that two or more classes can be of the same type and used interchangeably.
Polymorphism is the idea that two classes can be of the same type and used interchangeably. Polymorphism is the idea that two or more classes can be of the same type and used interchangeably. Polymorphism is the idea that two or more classes can be of the same type and can be used interchangeably.
Understanding the four pillars is the first step towards mastering any object-oriented programming language, and by taking advantage of the concepts exposed by these pillars, you can write software that is scalable, clean, and as bug-free as possible. Thanks for watching. I hope you learned something, and I'll see you next time.
Thanks, Mike. Appreciated it. Goodness, get this guy off my screen. I'm tired of this commercial. Have we had enough videos and articles? Let's go. Introduction to Object-Oriented Programming. In programming, most languages offer various features that give us different ways to tackle technical problems. With so many different languages out there, with their own unique set of features, it became necessary to create a classification system to help distinguish those sets of features. This ultimately led to the creation of the term programming paradigm, a way to classify different programming languages and the unique features that they offered. As we explore Python deeper, our code might fall into multiple paradigm categories at once. This is because most modern-day languages offer more than one specific paradigm we can program in. While we could spend all day exploring all the paradigms Python offers, we will instead dive into one of the most popular paradigms, and one we have already been using, maybe unknowingly, called Object-Oriented Programming, OOP. At the forefront of any language classified as an object-oriented programming language, there must exist the ability to create programs around classes and objects. We have already started working with these concepts earlier as we built our own custom classes, class methods, and instance objects. To recap, let's take a look at an example. Class dog sound equals woof. Def init self name age. Self.name equals name. Self.age equals age. Def bark self. Print dog.sound. So what this is doing, right? The def init makes sure that whenever we call a new dog object, we can pass it a name and an age, and the name and age that we pass it become the name and age as they're referred to in the rest of the class. We define this bark function, which takes in self, which means it doesn't really need to take in anything when we're calling the class elsewhere. If we have a dog object called poodle, we could just do poodle, and it'll just print woof. In the above example, we are representing, a poodle.bark, right? Yeah. We could just do poodle.bark and it'll just print woof. In the above example, we are representing a real-world entity, a dog, as a class with properties name and age and methods bark. These features make up the core of the OOP paradigm and ultimately allow us to build more intricate programs. This, however, only scratches the surface of what we can accomplish. To explore the paradigm further, we will examine the four core pillars of object-oriented programming: inheritance, polymorphism, abstraction, encapsulation. Each of these pillars will allow us to expand our skills so that we can take full advantage of the power of object-oriented programming in Python. We will begin exploring these pillars in later exercises, but for now, let's refresh ourselves on object-oriented programming fundamentals. First, to start our exploration into OOP, create a class that will represent an employee of a company. So, define a class called class employee. Define a class variable new ID and set it equal to 1. Each employee instance will need its own unique ID. Inside the employee class, define an init method Oops. Inside init, define self.id. So self ID and self.id equals, instead of equal to the class variable new ID. Lastly, increment new ID by 1. Init missing one required positional argument ID. So am I not supposed to pass itself? Expected class employee to be defined. Init missing one required positional argument new ID. Oh. Confused. This is why I don't understand object-oriented programming. So we have this class employee. Define a class variable new ID and set it equal to 1, right? We did that. Each employee instance will need its own unique ID. Inside the employee class, define an init method. Inside init, define self.id and set it equal to the class variable new ID. Lastly, increment new ID by 1. I don't want to view the solution. New ID plus equals 1. Maybe we don't do that within the init. Expected employee to be defined class employee. Def self.id equals new ID. New ID plus equals 1. Alright, tell me. Okay, wait. Just, yeah, keep my code. I don't want to look at anything else. Okay, now I should look at something else. So I got the first line wrong. I needed the parentheses. New ID equals that. Def init self, okay. Self.id equals employee.newID. Okay. So you can't refer to, so just doing new ID, it's out of scope, I guess. Inside init, define self.id and set it equal to the class variable new ID. So self ID equals employee.newID. Lastly, increment new ID by 1. And I thought that was needed to be in the init, but maybe not. Still think it needs to be in the new init. You set attribute self ID equal to employee.newID and the increment employee.newID by 1. I see. Now create a function. What would it have said? Define init inside, define self.id and set equal to employee.newID, then add 1 to employee.newID. Use the following syntax. I'm gonna get some explanation on this. Tell me why. The key difference between the two snippets is how they access and modify the new ID variable, which is a class variable. In the first correct snippet, self.id equals employee.newID accesses the new ID class variable correctly using class name.variablename, which is the right way to access class variables. Employee.newID plus equals 1 correctly modifies the new ID class variable by referring to it with class name.variablename, ensuring that the new ID is updated for the class itself, not just for an instance. In the second incorrect snippet, self.id equals new ID attempts to access new ID as if it were a local or instance variable, which it is not. correct way to access a class variable is by prefixing it with the class name employee.newID. NewID plus equals 1 attempts to modify NewID as if it were accessible in the local scope. However, since NewID is a class variable, this operation is trying to assign to a variable that hasn't been defined in the method scope. The correct way to modify a class variable is by accessing it with the class name .variable, as in employee.newID plus equals 1. The first snippet correctly uses the class name to access and modify the class variable, ensuring the variable is shared across all instances of the class. The second snippet incorrectly assumes NewID can be accessed and modified like a local or instance variable without specifying the class name, leading to a scope resolution error. Okay, makes sense. Now, create a function to output the instance ID. Inside the employee class, define a sayID method. Inside sayID, output the string my ID is, and then the instance ID. So output it, meaning print it. Did you put self as a parameter? Just, oh, I see. Did you put, I'll put a message of self.id. Ah, okay. Okay. So because we set employee.newID to self.id here in the init function or the init method, then we can pass self.id to this other method because we're passing self to the method. So it can access self.id. And I misspelled ID here. And then the instance ID. Lastly, create two employees and have them give their IDs. E1 equals new employee. Let's create two employees and have them give their IDs. Outside of the employee class, define the variable E1 and set it to an instance of employee. Define the variable E2 and set it to an instance of employee. Have both E1 and E2 output their IDs. Or invalid syntax. Do I need this? E1 equals new employee. Oh, you don't have to put new. I think I might be getting C++ and Python confused. Maybe I'm just dumb. Oh, I see. Self.id gets passed as what you want to call it, an integer. Cool. So we can create a class employee. So that's how you create a class name parentheses. We define a class variable, new ID equals 1. We initiate the class def init self. We pass the class itself to the init method. Self.id equals employee.newID. Employee.newID plus equals 1. Def say ID self. Print my ID is plus string self.id. So now we can create a new employee. E1 equals employee. So E1 is an employee. E2 is an employee. When we run E1.sayID, it's running this class the method from the class say ID self, which prints my ID is string self.id. And every time we run this, because every time we initialize a class, every time we initialize a new employee, the ID initialization method of employee assigns the employee.newID to self.id and then increments employee.newID by 1. Makes sense. Object-oriented programming pillar, inheritance. When we hear the word inheritance, code may not be the first thing that springs to mind. We're probably more likely to think of inheriting genetic traits like the eye color from a mother or dimples from a grandfather. In the world of object-oriented programming, inheritance is actually one of the core pillars for creating intricate structures with our classes. To dive into this concept, let's examine a dog and cat class. Class dog, def bark, self, print wolf. Class cat, def meow, self, print meow. These classes define two distinct animals with their own methods of communication. Now, what if we wanted to give both of these classes the ability to eat by calling a method called eat? We could write the method twice in both classes, but then we would be repeating code. We also might need to write it inside every specific animal class we ever create. Instead, we can utilize the power of inheritance. Since both cat and dog fall under the classification of animal, we can create a parent class to represent properties and methods they can both share. Here's what it might look like. Class animal, def eat, self, print, nom nom nom, eating food. Great, we have an animal class with an eat method, but how do we actually get the dog and cat class to inherit this method so it can be shared with both classes? Well, here's what the base structure will look like. Class parent class with the class methods and properties, class child class, and inside the parentheses we pass the parent class, and then we write out the class methods and properties of the child class. We can, if we apply this structure to our example, our code looks like this. Class dog, animal, def bark, self, print bark. Class cat, animal, def meow, self, print meow. Now, let's see inheritance in action. Fluffy equals dog, Zoomy equals cat, Fluffy.eat, nom nom nom, eating food, Zoomy.eat, nom nom nom, eating food. As we can see, there are some clear advantages of utilizing inheritance. Not only are we able to reuse methods across multiple classes using our parent class, we are also able to create parent-child relationships between entities. Now that there is an employee class, we want to make a more specific type of employee, admin. In script.py, create an admin class that inherits from the employee class. Inside the body of the class, insert the pass statement. So, class admin inherits employee, and create an admin class that inherits from the employee class. Inside the body of the class, insert the pass statement. So, pass. Now it's time to test out your inheritance implementation. At the bottom of script.py, define a variable e3 and set it to an instance of the admin class. Now if you call the say.sayId, so e3.sayId, method of the admin instance in E3, you will get output of the instance's ID. Nice. Overriding methods. When implementing inheritance, a child class may want to change the behavior of a method from its parent class. In Python, all we have to do is override a method definition. An overriding method in a subclass is one that has the same definition as the parent class but contains different behavior. So here we see class animal, def init, self name, self.name equals name, def make noise, self, print, curly braces says ger.format, self.name. So this will pass the name into the curly braces. Pet1 equals animal, and we're passing it rex. So this gets assigned as the name, becomes self.name equals name, and then we run pet1.make noise. And since we already initialized this pet by passing it its name, when we run pet1.make noise, it formats self.name into these curly braces, and we get rex says ger. The animal class above has one attribute, self.name, and one method, .makeNoise. The .makeNoise method outputs a somewhat generic animal sound. Rex says grr. If we define a subclass of animal, we may want to make a different sound. Class cat is an animal, def makeNoise self, print curly braces says meow, .format self.name. Pet2 equals cat, Maisie. Pet2 makeNoise, Maisie says meow. Now we've made a class for a more specific type of animal, cat. It has all the attributes and methods of animal. However, if you call the makeNoise method on this instance of cat, it will say Maisie says meow. As an admin, you feel it is not important to give your ID, but just let others know they're talking to an admin. Inside the admin class, define a method, say ID. Inside the method, output I am an admin. Now when you call .sayId with E3, you should see the .sayId method output from admin. So again, as an admin, you feel it is not important to give your ID, but just let others know they're talking to an admin. Inside the admin class, define a method, say ID. Inside the method, you gotta pass self. Inside the method output, I am an admin. Okay. Now when you call .sayId with E3, you should see the sayId method output from admin. I am an admin. And one thing to note is that you don't have to write the init method with this inherited class because it's already inheriting the initialization from employee. Super. When overriding methods, we sometimes want to still access the behavior of the parent method. In order to do that, we need a way to call the method of the parent class. Python gives us a way to do that using super. Super gives us a proxy object. With this proxy object, we can invoke the method of an object's parent class, also called its superclass. We call the required function as a method on super. So here we have class animal, def init, self, name, sound equals grr, self.name equals name, self.sound equals sound, def makeNoise, self, print, curly brace says curly brace dot format self.name, self.sound. Class cat is an animal, def init, self, name, super dot init, name, meow. Pet cat equals cat, Rachel, pet cat dot makeNoise, Rachel says meow. So again, when overriding methods, we sometimes want to still access the behavior of the parent method. In order to do that, we need a way to call the method of the parent class. Python gives us a way to do that using super. Super gives us a proxy object. With this proxy object, we can invoke the method of an object's parent class, also called its superclass. We call the required function as a method on super. So here, for the initialization of our cat animal, whereas in animal, it's initialized with self.name equals name and self.sound equals sound. In our initialization for cat animal, we run super.init name and meow. And again, super gives us a proxy object. With this proxy object, we can invoke the method of an object's parent class, also called its superclass. We call the required function as a method on super. So it's invoking this with the super. In the above example, we have the class animal and the subclass cat. Animal has two attributes, name and sound, and one method, makeNoise. The makeNoise method outputs the name and sound of an instance. The cat subclass has an init method, which means the init method of its superclass, animal, will not be called when creating an instance of cat. The init method from the subclass is overriding the one from the superclass. To still invoke the init method of animal, super init name meow is called inside the subclass init method. This additional logic allows us to add the meow sound from within the cat class, but still use the init method of the animal class. Super is used in subclasses to invoke a needed behavior from the superclass alongside the behavior of a subclass method. Once the managers found out that the admins were walking around just telling people they are admins, the manager stepped in and made them also say their ID. Inside the admin class, add a line that also calls the employee class .sayID method. Now the output should be the admin's ID and that they are an admin. So inside the admin class, add a line that also calls the employee class .sayID method. So I guess we do super dot say ID and we pass it self. So in this case, in order to use the make noise function from animal, but override the sound that it makes, and the sound it makes is set in the init. We did a new an init within cat and passed itself a name. And within that, instead of defining a self.name name, self.sound, we can take these from the superclass, from the superclass's initialization, and pass it name and meow instead. So for here, in the superclass's sayID function, it prints my ID is dot format self dot ID. So we can do super sayID and pass it. I'm a little confused here. Pass it self? No, sayID takes one positional argument, but two were given. Oh, we don't need to pass it anything. If we just do super.sayID within our sayID, then it'll run this print statement. Yeah. Use super to call the employee class.sayID method. Use the following syntax. Super.sayID. Cool. Multiple inheritance part 1. Let's now look at a feature allowed by Python called multiple inheritance. As you may have guessed from the name, this is when a subclass inherits from more than one superclass. One form of multiple inheritance is when there are multiple levels of inheritance. This means a class inherits members from its superclass and its superclass. Again, let's now look at a feature allowed by Python. Am I running good on time? Yeah, I'm fine. Let's now look at a feature allowed by Python called multiple inheritance. As you may have guessed from the name, this is where a subclass inherits from more than one superclass. One form of multiple inheritance is when there are multiple levels of inheritance. This means a class inherits members from its superclass and its superclass. So here we have class animal, def init, self name, self.name equals name, def say hi, self print, curly brace says hi, dot format, self.name, class cat animal pass, class angry cat pass, my pet equals angry cat, Mr. Cranky. My pet dot say hi, Mr. Cranky says hi. In the above example, angry cat inherits from cat and cat inherits from animal. Both angry cat and cat have access to the animal class name attribute and dot say hi method. Any feature added to cat, angry cat will also have access to. Managers decide to start walking around more to let people know who's in charge. Inside script.py, define a manager class. Write your code below. And have it inherit from the admin class. Inside the manager class, define a method, say ID. Inside the manager class, define a method, say ID that outputs that they are in charge. So print, I'm in charge. Did you define the manager class? I thought I did. Oops. Set the manager class, define a method, say ID. outputs that they are in charge. Oh, my fault. I defined a manager function. The managers want to set a good example, so they also let people know their ID and that they are an admin inside the .sayId method of manager. Call the admin class .sayId method. So super .sayId. Now test it out. At the bottom of script.py, define a variable e4 and set it to an instance of the manager class. Call the sayId method of the instance in e4. Now you will get output from all three classes. My ID is 4, I'm an admin, I'm in charge. Multiple inheritance part 2. Another form of multiple inheritance involves a subclass that inherits directly from two classes and can use the attributes and methods of both. So here we have class animal, def init self-name, self.name equals name. Class dog is an animal, def action, self, print, curly braces, wags, tail.all.format, self.name. Class wolf is an animal, def action, self, print, curly braces, bites.ouch, format, self.name. Class hybrid is a dog and a wolf, def action, self, super action, wolf.action, self. My pet equals hybrid fluffy. My pet.action, fluffy wags tail, aw, fluffy bites, ouch. So this super.action activates from this dog class, and this wolf.action past self operates from this wolf class. So I wonder if this is due to the order, the fact that it's a dog first and then a wolf, that you can call the dog action by just doing super.action. But in order to call the wolf action, you have to specify wolf.action and pass in self. Let's see. The above example shows the class hybrid is a subclass of both dog and wolf, which are also both subclasses of animal. All three subclasses can use the features in animal, and hybrid can use the features of dog and wolf, but dog and wolf cannot use each other's features. This form of multiple inheritance can be useful by adding functionality from a class that does not fit in with the current design scheme of the current classes. Care must be taken when creating an inheritance structure like this, especially when using the super method. In the above example, calling super.action inside the hybrid class invokes the .action method of the dog class. This is due to it being listed before wolf in the hybrid dog-wolf definition. The line wolf.action self calls the wolf class.action method. The important thing to note here is that self is passed as an argument. This ensures that the .action method in wolf receives the hybrid class instance to output the correct name. Makes sense. Admins in the company need access to the consumer-facing website. This means that admins must also be users of the site. The class user has been added and has the attributes username and role and the .sayUserInfo method. To get the admins the user access they need, have the admin class inherit from the user class alongside the employee class. Be sure to have the employee class listed first in the admin class definition. So again, admins in the company need access to the consumer-facing website. This means that admins must also be users of the site. The class user has been added right here and has the attributes username. So pass username and role customer, self.username equals username, self.role equals role, def say user info self, print my username is curly braces.format self.username, print my role is curly braces.format self.role. The class user has been added and has the attributes username and role in the .say user info method. To get the admins the user access they need, have the admin class inherit from the user class alongside the employee class. Be sure to have the employee class listed first. So employee user. Now let's make sure the admins get their user data set up. Inside the init method of the admin class, call the init method of the user class. So user.init self. Init missing one required positional argument username. hard to find. So here, username. Sorry. Inside the init method of the admin class, call the init method of the user class. Pass the admin class instance ID and the string admin as arguments. So self.id will be their username. And admin will be their role. Confirm the user data is set up correctly. Call the say user info method using the admin instance in E3. So E3 dot say user info. My username is 3. My role is admin. Object-oriented programming pillar, polymorphism. In computer programming, polymorphism is the ability to apply an identical operation onto different types of objects. This can be useful when an object type may not be known at the program runtime. Polymorphism can be applied using Python in multiple ways. We've already experienced a form of it when exploring inheritance. Class animal, def init, self, name, self.name equals name, def make noise, self, print, curly braces says ger.format, self.name, class cat, animal, def make noise, self, print curly braces says meow, dot format, self.name, class robot, def make noise, self, print beep.boop, beep. The example above shows an animal class, its subclass cat, and another standalone class robot. Each class has a method .make noise with different outputs. The identical method name with different behaviors. The identical method name with different behaviors is a form of polymorphism. An animal equals animal bear. My pet equals cat Maisie. My vacuum equals robot. Objects equals an animal, my pet, my vacuum. For O in objects, O.make noise. And the output is bear says grr, Maisie says meow, beep.boop, beep. With the classes instantiated and added to a list, we are able to iterate through the list and call .make noise. This is done without needing to know what type of class .make noise belongs to. A meeting needs to be scheduled with at least one employee, one admin, and one manager. Define a variable meeting and set it equal to a list that contains variable. Meeting, set it equal to a list that contains an instance of each class, employee, admin, and manager. Okay. So employee equals employee, admin equals admin, manager equals manager, employee, admin, manager. Expect the instance of manager to be in list meeting. Did I misspell it? With the different types of employees in the meeting, have them all say their ID. So for person in meeting, person dot say ID. Using a for loop, iterate through the list meeting using your defined loop variable. Call the say ID method on each instance of the list. My ID is 1, my ID is 2, I'm an admin, my ID is 3, I'm an admin, I'm in charge. Dunder methods. The code below shows that when working with different object types like int, string, or list, the plus operator performs different functions. This is known as operator overloading and is another form of polymorphism. For an int and an int, plus returns an int. 2 plus 2 is equal to 6. For a string and a string, plus returns a string. Is this plus addition equals or is equal to is this addition? For a list and a list, plus returns a list. List 1, 2 plus list 3, 4 is equal to list 1, 2, 3, 4. To implement this behavior, we must first discuss dunder methods. Every defined class in Python has access to a group of these special methods. We've explored a few already: the constructor, init, and the string representation method, repr. The name dunder method is derived from the double underscores that surround the name of each method. Recall that the repr method takes only one parameter, self, and must return a string value. The returned value should be a string representation of the class, which can be seen by using print on an instance of the class. Review the sample code below for an example of how this method is used. Defining a class's dunder methods is a way to perform operator overloading. So class method def dunder init self name self.name equals name, def dunder repr self return self.name, def add self another animal return animal self.name plus another animal.name. A1 is an animal called with the name of horse. A2 is an animal with the name of penguin, and A3 equals A1 plus A2. And because we created this dunder add method with self and another animal, when we add one animal to another, it returns animal self.name, so the animal's name and another animal's name. Okay, so I think this name is kind of arbitrary of another animal, but it's just saying when we add one animal to another animal, it returns each of their names. So print A1 prints horse, print A2 prints penguin, print A3 prints horse penguin. The above code has the class animal with the dunder method, dunder add. This defines the plus operator behavior when used on objects of this class type. The method returns a new animal object with the names of the operand objects concatenated. In this example, we have created a horse penguin. The line of code A3 equals A1 plus A2 invokes the .add method of the left operand A1 with the right operand A2 passed as an argument. The name attributes of A1 and A2 are concatenated using the .add parameters self and another animal. The resulting string is used as the name of a new animal object, which is returned to become the value of A3. There is now a meeting class with an attendees list attribute and an add dunder method that adds employee instances to the attendees list. Before we try and add employees to a meeting, we want to make sure we can know how many employees are in a meeting. Inside the meeting class, overload the len operation. So overload the len operation by defining a len dunder method. So def dunder len self. Inside the len definition, return the length of the attribute attendees. Return so length takes in self and takes in meeting.attendees, right? No, it's just self.attendees. Return the length of self.attendees, and then so the return the length of the attribute. Okay, so no, not self. Did you define the dunder method len inside of the meeting class? I thought I did. Self attendees, return length of attendees. There is now a meeting class with an attendees list attribute and an add dunder method that allows employee instances to the attendees list. That adds employee instances to the attendees list. So add self employee print ID curly braces added dot format employee dot ID self dot attendees dot append employee. Write your code def len self attendees. I think maybe okay. Now add 3 employees to a meeting. Using the meeting instance, M1, add each of the employee instances E1, E2, and E3. Use one line for each employee instance. Output the length of meeting instance 1. So add 3 employees to a meeting. So M1, so add self employee, print ID added, format employee ID. So when we initialize M1 as a meeting, it gets a dot attendees. For some reason, the more I say that word, it just sounds silly. Self.attendees is an empty list. And then we add self and an employee, print ID. So M1 plus E1, output the length of meeting instance 1. You should see the output from each employee being added. Using the meeting instance M1, add each of the employee instances E1, E2, and E3. Use one line for each employee instance. So output the length of meeting instance. So print len M1 plus E1. I don't think this is right. Kind of throwing crap at the wall. Object of none type has no len. If we do I'm a little bit confused and running very short on time, so let's get a hint. With M1 as the left operand, add E1, E2, and E3 to M1. Then output the length of M. Oh, I honestly didn't think I could just do that. Cool. Object-oriented programming pillar, abstraction. When a program starts to get big, classes might start to share functionality, or we may lose sight of the purpose of a class's inheritance structure. In order to alleviate issues like this, we can use the concept of abstraction. Abstraction helps with the design of code by defining necessary behaviors to be implemented within a class structure. By doing so, abstraction also helps avoid leaving out or overlapping class functionality as class hierarchies get larger. From ABC, import ABC abstract method, class abstract, or I'll focus on this one. From ABC, import ABC abstract method. Class animal is an instance of ABC. Def init self name, self name equals name, with a decorator abstract method, which we imported. So we're importing an abstract method function, and we have this def make noise self, which does nothing. Class cat is an animal. Def make noise self print curly braces says meow dot format self dot name. Class dog is an animal. Def make noise self print curly braces says woof dot format self dot name. So kitty equals cat with the name Macy, and doggy is a dog with the name Amber. Kitty dot make noise, Macy says meow. Doggy dot make noise, Amber says woof. Above we have cat and dog classes that inherit from animal. The animal class now inherits from an imported class ABC, which stands for abstract base class. This is the first step to making animal an abstract class that cannot be instantiated. The second step is using the imported decorator at abstract method on the empty method dot make noise. The below line of code would throw an error. An animal equals animal scruffy. Type error can't instantiate abstract class animal with abstract method make noise. The abstraction process defines what an animal is, but does not allow the creation of one. The init method still requires a name, since we feel all animals deserve a name. The dot make noise method exists since all animals make some form of noise, but the method is not implemented since each animal makes a different noise. Each subclass of animal is now required to define their own make noise method, or an error will occur. These are some of the ways abstraction supports the design of an organized class structure. Take a look at the code in script.py. The abstract class abstract employee is defined. It has all the logic that has previously existed in the employee class. New ID equals 1, definite self, self.id, abstract employee.new ID, abstract employee.new ID plus equals 1, abstract method, def say ID, self, pass, write your code below, class employee pass, E1 is an employee, E1.sayId. The employee class currently has no implementation. Take a look at the code in script.py. The abstract class abstract employee is defined. It has all the logic that has previously existed in the employee class, except that the .sayId method is not implemented and has the abstract method decorator. The employee class currently has no implementation. Run the code and observe that E1 sayId is causing an attribute error since the employee class has no implementation. Employee object has no attribute sayId. Let's fix this error. Make the employee class inherit abstract employee class. Nice work, but wait, there's still an error. Can't instantiate abstract class employee with abstract method sayId. The .sayId method in the abstract employee class uses the abstract method decorator. This means any class that inherits from abstract employee must implement a sayId method. Inside the employee class, replace the pass statement then. Define a sayId method that outputs a message with self.id. Invalid syntax. Hi, 1. Object-oriented programming pillar, encapsulation. Encapsulation is the process of making methods and data hidden inside the object they relate to. Languages accomplish this with what are called access modifiers like public, protected, private. In general, public members can be accessed from anywhere. Protected members can only be accessed from code within the same module, and private members can only be accessed from code within the class that these members are defined. Python doesn't have any inbuilt mechanism to prevent access from any member, i.e., all members are public in Python. However, there is a common convention amongst developers to use a single underscore self._x to indicate that a member is protected. Accessing a protected member outside of the module will not cause an error. It is added by developers to inform other developers that they should be careful when accessing this member in such a manner. Similarly, we can declare a member as private with two leading underscores, self dot, double underscore x. This is more than just a convention in Python because of a mechanism called name mangling. Members that are preceded with two underscores have their names modified in the background to object._classname double underscore x. While they can still be publicly accessed, the purpose of this mechanism is to prevent clashing member names of any inheriting classes that might define a member of the same name. Note that this is different from the dunder methods we discussed earlier. A dunder method has two leading and two trailing underscores and is treated differently than a private member. One important difference is that dunder method names are not mangled. The employee class contains one attribute, ID. Okay, let's breeze through it. The employee class contains one attribute, ID. An instance variable e is defined and then passed to the function dir, which is output to the console. Employee contains one attribute, ID. An instance variable e is defined and then passed to the function dir, which is output to the console. Dir is a built-in Python function that returns a list of all class members, including dunder methods. When you run the code, you will see a list of class methods with ID as the last element. Now add an attribute that uses the single underscore naming convention. Self. Inside the employee class, a init method define the single underscore variable ID and set it equal to whatever you want. I don't know, 5. When you run the code, you can see ID as the second to last element, or underscore ID as the second to last element. The output list now define a variable using the double underscore self dot double underscore ID. Set it equal to whatever you want. Make it 6. When you run the code, you can see a new variable employee ID as the first element in the output list. This is the result of name mangling the variable self ID. Getters, setters, and deleters. Using getter, setter, and deleter functions are one way to implement encapsulation within Python, where the state of class attributes can be handled within the class. These functions are useful in making sure that the data being handled is appropriate for the defined class functionality. Class animal, def init, self name, self dot underscore name equals name, self dot underscore age equals none. Def get age, self, return self dot underscore age. Def set age, self new age is instance, if is instance new age int. So if new age is an integer, self dot underscore age equals new age, else raise type error. Def delete age, self print underscore age deleted, del self dot underscore age. Looking at the animal class above, there is an underscore age attribute with a single underscore. This notates it is intended to be used only within the module. There are then 3 methods related to age, each with a different purpose. These define the getter, setter, and deleter of the specific property. The first method related to age is a getter and returns self.age. The setter is implemented below that. It includes logic that ensures that the value passed to new age is an integer. If so, self._age equals new age. If not, raise an error. This is useful and shows the power of using these functions for encapsulation. The deleter is implemented below the setter. It outputs a confirmation message and uses the del keyword to delete the self._age attribute. A equals animal Rufus, print a.getAge, none. A.setAge 10, print a.getAge 10. A.setAge 10 as a string raises a type error. A.deleteAge, age deleted, print a.getAge raises an attribute error. Above, we set a.getAge. We see a.getAge gets the underscore age value. A.setAge 10 sets the value, and a.deleteAge deletes the attribute entirely. A type error occurs with a.setAge 10 as a string because the defined logic in the setter is looking only for an integer. An attribute error occurs with a.getAge after the attribute was deleted. Using a getter, setter, and the single underscore naming convention, the employees of the company will now be able to use their names. The single underscore attribute underscore name has been added to the employee class right here. Names default to none unless a string argument is passed during instantiation. Inside the employee class, define a getter method called getName. So def get name self that returns the class attribute name. Get name return self dot name, right? Yeah. What did I do wrong? Invalid syntax. Colon. Add a setter method inside the employee class. Def set name. Self. Define a setter method set name that has an additional parameter for the name string. So the setter method. So I guess just name string. And sets the class attribute name. Self.name. And okay. Damn it, I gotta go. Self.name equals name string. Is that right? Does set name self.name to a new value underscore. Lastly, add a deleter method inside the employee class. Define a deleter method named del name that deletes the attribute. Colon. Great job defining getter and setter. Uncomment the code at the bottom of script.py to test it out. Whatever. All right, review. Congratulations. You've completed the object-oriented programming with Python lesson. Let's do a quick recap of what you learned. We discussed the 4 pillars of object-oriented programming as they apply to the Python programming language inheritance. Python allows classes to inherit on multiple levels, meaning a class can inherit from a base class as well as a derived class. Python also supports multiple inheritance, where one class can inherit from any number of other classes. This allows us to describe complex relationships between objects with minimal repeated code. Polymorphism. Polymorphism is a concept that allows functions and objects to behave in different ways depending on context. There is the polymorphism of functions like len or the addition operator plus, which can act differently depending on the provided data. Abstraction. Python supports the concept of abstraction by allowing objects with methods that have the same name to be called in a general manner. Further, Python provides the abstract base class ABC for us to create a more clearly defined interface. Encapsulation. Python's approach to encapsulation is unique compared to most other object-oriented programming languages. In Python, all members of an object are publicly accessible, but there are conventions to indicate to developers that a member is intended to be protected or private. In this lesson, we learned more complicated relationships between classes. We learned how to create a subclass of an existing class, how to redefine existing methods of a parent class in a subclass by overriding them, how to leverage a parent's class's methods in the body of a subclass method using the super function, how to write programs that are flexible using interfaces and polymorphism, how to write data types that look and feel like native data types with dunder methods. These are really complicated concepts. It's a long journey to get to the state of comfortably being able to build class hierarchies that embody the concerns that your software will need. Give yourself a pat on the back. You earned it. Take a look at the code in script.py. We've added a complete example that aligns with the 4 pillars of object-oriented programming. Can you identify each one within the class interactions?